To truly understand how YugabyteDB works, we need to take a look at the core building blocks that makes this distributed system work. And we will understand the core components and terminology which include the physical server or nodes which make the cluster and universe. We'll also discuss about the logical shards called tablets and the processes that manage data replication and metadata. Each of these components plays a vital role in ensuring YugabyteDB delivers high availability, strong consistency, and linear scalability. Now let's dive into each of these components. So we'll start with the most fundamental one, which is the node. A node in YugabyteDB refers to an individual server. The server can be a physical or a virtual server, and this node will be part of a database cluster. So few nodes together will form a cluster. Each node has its own compute, memory, storage, network resources, which collectively will be the total cluster resources. So multiple nodes bringing their own compute, storage, memory, and network. Together, all these nodes resources will be the total cluster resources. So every node typically runs two main background processes. One is YB master, also known as master server process, which is responsible for metadata and cluster coordination. And the second process is called yb-tserver, or also known as tablet server, which handles actual data storage and query execution. Nodes are the fundamental building blocks of a YugabyteDB universe. They work together to distribute the data, ensure high availability, and support horizontal scaling. As you add more nodes to a cluster, YugabyteDB automatically redistributes tablets and balances the load across the nodes. In production deployments, nodes are usually spread across multiple availability zones or regions to provide fault tolerance and resilience against failures. So that brings us to the next core component which we already touched based upon, which is a universe. In YugabyteDB, a universe refers to a complete and self-contained deployment of a YugabyteDB cluster. It includes all the configuration settings, nodes, regions, replication factor, and operational policies needed to run a database environment. A universe at the highest logic, you can also think about the universe as a highest level logical unit in Yugabyte Anywhere, which is called YBA. So the universe represents everything which is required for one application or a workload. So within a universe, you can have a primary cluster for handling all the reads and writes, and optionally one or more read replicas in a remote regions, which can serve read-only traffic with providing lower latency. Because universes are isolated from each other, they provide a clean way to organize and manage multi-tenant or multi-environment deployments while still using the same Yugabyte Anywhere platform, which is a YBA platform. So now let's move on to the one of the important component, which is a master process, which is also known as YB master. So this YB master is one of the two core processes that run on Yugabyte DB node. It acts as a control plane of the database cluster, managing all metadata and coordination tasks. Its key responsibilities include tracking tables, tablets, users, roles, permissions, as well as coordinating operations like table creation, tablet placement, load balancing, and other cluster configuration changes. So this YB master is also responsible for tablet to node mapping. So when a client sends a request, it knows which node to route the query to. This improves the performance and efficiency. To ensure high availability and fault tolerance of this YB master process, this runs as a Raft consensus group, typically with three nodes. One master acts as the leader while the others serve as the followers, ready to take over if the leader fails. So in short, we can think of YB master as the cluster's brain. It handles coordination, metadata management for data nodes or tablet servers, So the other nodes, data nodes and tablet servers can focus on storing and processing of the actual data rather than worrying about managing the metadata and where the tables should be, where the tablet should be, all how the routing should happen. All these things are taken care by the YB master process. So now let's move on to the next important core component, which is the tablet server, also known as T server or YB-tserver. So this tablet server is the data plane component of the YugabyteDB. It's responsible for storing data, executing queries, and handling client requests. Each YBT server manages one or more tablets, which are shards of the tables. These tablets are stored internally using RocksDB, which is a high performance key value store. When a query comes in, whether it's from YSQL API or YSQL API, the tablet server is responsible for parsing, planning, and executing that query. It can serve requests directly if the data is local or coordinate with the other nodes when needed. The tablet server also participates in a Raft consensus groups for each tablet it hosts. One of the tablet peer is elected as the leader to handle all writes, ensuring strong consistency and replication across the cluster. In addition, YB-tserver handles background tasks like compaction, wall management, and query caching, which help keeps the performance optimal. Overall, we can think of YB-tserver as the worker of the cluster. It does the heavy lifting for data access, replication, and processing. So now let's move on to the most important core component, which is the tablet, and which is the main differentiator for a traditional databases versus distributed database. In YugabyteDB, a tablet is a shard of a table. When a table is created, it is automatically divided into multiple tablets based on the split criteria. This sharding allows the database to scale horizontally by distributing tablets across multiple nodes. Each tablet contains a subset of tables rows and is stored as a RocksDB instance on a particular node. So this design enables parallel processing and efficient data access. Every tablet belongs to a Raft consensus group, typically consisting of 3 replicas generally. One replica acts as the leader, which handles all write operations for the tablet, and the other replicas for the same tablet are known as followers, ensuring high availability and consistency. As more data is inserted or workload increases, YugabyteDB can automatically split these existing tablets into further more tablets to maintain performance. So this fine-grained partitioning is the key to YugabyteDB's ability to scale and balance load across the cluster. So in simple terms, tablets are the core units of storage and replication in the YugabyteDB, making distributed SQL work efficiently behind the scenes. So moving on, we already touched upon Raft consensus group a few times already. In YugabyteDB, each tablet is managed by a Raft consensus group. This is the key mechanism that ensures strong consistency and fault tolerance across a distributed system. A Raft group consists of multiple replicas of the same tablet, typically 3 if the replication factor is set to 3. One replica is elected as the leader and the other acts as the followers. All write operations go through the leader, which replicates the changes to the followers. Only after a majority of replicas confirm the operation, it is considered committed. This ensures that data is never lost even if a node fails. If the leader node goes down, the remaining nodes in the Raft group automatically elect a new leader, keeping the system highly available without human intervention. So this Raft-based approach guarantees consistency. Every node eventually agrees on the same state of the data and also enables automatic failover and resilience against node failures. So in simple terms, we can consider a Raft group that it ensures data in the each tablet is always consistent, available and safe no matter what happens to the individual nodes. So that brings us to the next core component, which is the replication factor, which we have already touched base few times. So the replication factor, also known as RF, In Yugabyte, this defines how many copies of each tablet are stored across different nodes in the cluster. For example, if the replication factor is set to 3, it means that each tablet has 3 copies, one on each of the 3 different nodes. Out of these replicas, one acts as the leader, which handles all writes and coordinates replication. The other two are followers, which stay in sync with the leader and can take over if the leader fails. So this replication model ensures high availability and fault tolerance. Even if one or two node goes down, the system continues to function without data loss. The replication factor also directly affects quorum based operations. For RF equals to 3, at least two nodes must agree, a majority, for a write to be considered successful. In production deployments, RF is usually set to 3, but it can be increased for greater resiliency, or it can be reduced in test environments to save resources. So let's move on to the next component, which is Yugabyte Anywhere, which is one of the most important or appreciated component once we go further into this training. So Yugabyte Anywhere or YBA is a centralized control plane which is used to manage YugabyteDB deployments across any infrastructure, whether it's on premises or in the cloud or in a hybrid environment. It has a user-friendly web UI and automation tools. So IBA simplifies complex tasks like provisioning clusters, scaling nodes, performing upgrades, monitoring, and performance metric review, and all these things. It also provides advanced features like role-based access control, TLS certificate management, metrics dashboards, alerting, to name few. All these are designed to help DBAs and SREs to manage distributed database environments with ease and consistency. Ultimately, YBA allows organizations to maintain enterprise-grade governance, visibility, and operational control across all Yugabyte universes regardless of where they are deployed. So finally, let's move on to the another important core component, which is a Yugabyte Smart Driver. Yugabyte Smart Driver is a Postgres compatible database driver that's been enhanced specifically for Yugabyte DB's distributed architecture. Unlike traditional PostgreSQL drivers, which are designed for single node databases, the Smart Driver is both cluster aware and topology aware. This means it understands the layout of Yugabyte DB cluster and intelligently routes connections. It automatically distributes application traffic across all healthy nodes, avoiding hotspots and improving performance through built-in load balancing. In geographically distributed deployments, it can route queries to the nearest available region, help reduce the latency. The driver also adapts to the cluster membership changes. So if a node is added, removed, or failed, the driver automatically updates its routing logic without requiring application changes or external load balancers. Overall, the Yugabyte Smart Driver simplifies application connectivity while boosting resilience, performance, and availability in the distributed environments. Alright, so with the core components brief understanding, let's try to look at a Yugabyte DB reference architecture and try to relate the core components in the architecture, and which should give us a better understanding and relate what exactly those means. So let's first start with nodes. So I think that's a simple concept, right? Nodes is just a VM or an Azure virtual machine, or if you're on-premise setup, then it is just an VM that you request from your infra team. So on this VM or a EC2 instance, you are going to have a bunch of nodes which are going to contain all your data which are sharded, and then you need one additional node for having a control plane. And nodes run multiple processes. One of the processes will be master server process, and another is T-server, tablet server process. So I think, yeah, the nodes concept is pretty simple. It's just a virtual machine or node. And then let's try to understand what exactly is a universe. So if you look at this diagram, I have represented two universes. One is a primary universe, which is the top part, and the below one is the DR universe. So a group of nodes are going to form an universe. And if you see the node 1, 2, 3, 4, 5, 6 at the primary site are forming one universe, we are just calling it as a primary universe, and the below node 1, 2, 6 we are calling as a DR universe. So technically you can just think there are two universes in this particular architecture. One is a primary universe and secondary universe. And then we are going to come back to a universe because there is some additional things that you need to understand. So the next thing that I'm going to discuss about is the cluster. So again, cluster is also a group of nodes. So here, although I have not explicitly mentioned, but there are two clusters here. One is the primary cluster, node 1 to 6 is primary cluster, and below node 1 to 6 are the DR cluster. Now you may have a doubt, like you just said node 1 to 6 is primary universe and node 1 to 6 down is a DR universe. Again you are saying node 1 to 6 is again a cluster and node 1 to 6 below is another cluster. So what exactly is the difference between a primary cluster and a primary universe versus DR cluster and DR universe? Because both of them are at the moment looking like similar. In this architecture, although I have not represented, but to clarify and get away with your confusion, a universe is having a 6 nodes, but a cluster can have multiple uh, clusters in a universe. Oh, maybe I'm confusing. So what I'll say is here, if you consider another architecture, node 1, 2, 3 will be one cluster, and you can have node 4, 5, 6 as a read-only cluster. So all your read write operations will go to node 1, 2, 3, whereas node 4, 5, 6 are going to take your read workloads. Then your universe will still be remaining as one universe, but you will have two clusters now in the one universe. That is node 1, 2, 3 forming a read write cluster versus node 4, 5, 6 forming a read only cluster. Also you can have like node 1 to 6, 1 2 3 4 5 6 as one cluster, and that is in primary universe, whereas in DR you can have node 1 2 3 as a another cluster and node 4 5 6 as a another read only cluster at DR. So DC will have 6 read write nodes, whereas in DR you can have 3 read write nodes and 3 read only. So DR will have two clusters, whereas primary universe may have one cluster. And another architecture is in primary you can have 1 2 3 as read only read write cluster and 4 5 6 as read only. Also in DR you can have 1 2 3 as read write and 4 5 6 as read only. So you are going to have total 4 clusters, 2 universe and 4 clusters. So what we have seen so far is one universe, one cluster, one primary universe, one cluster, one DR universe, one cluster, or one primary universe, two clusters, one DR universe, one cluster, or one primary universe, two clusters, and one DR universe, two clusters. So all these kind of possibilities can be done, and I hope that now gives you a difference between what exactly is a cluster versus universe. So the universe will be all the nodes which can be multiple clusters together will form a universe. The cluster will be either a read write cluster or read only cluster. So with that, let's move further. So I touch based upon what is a master server process and T server process. So let's first see what is a master server process here. So any cluster or a universe mandatorily should have a master server process. Again, as this is a distributed architecture, any process should have redundancy and should follow replication factor. So if you consider default replication factor of 3, you should have, even though you have 6 nodes, you should have at least 3 primary server process or master server process. So here in this reference, if you see, if 1 2 3 nodes have master server process, then 4, 5, 6 will not have master server process, whereas 1, 2, 3, 4, 5, 6 can have t-server process. Hope that is not confusing, but let me reiterate again. With replication factor 3, you need to have a master server process running at least on 3 nodes. One will serve as a primary and the two are followers. We already discussed briefly what exactly is the responsibility of master server process. It holds metadata and it takes care of routing the connections, all this stuff we have already talked about, right? So now the reason why we have 3 master server process, one primary, 2 followers, is to ensure we have a high availability and redundancy. So even if the node 1, which is a master process of the master leader of the master server process, goes down, automatically node 2 and node 3 will form a Raft consensus and elect a new leader. So let's say node 2 has been elected as a new leader. In that case, node 2 will have the master server process, which was earlier follower, will become a primary master server process. And then still to ensure high availability, it has to again elect a new leader. Let's say node 1 has not come online, then node 2 and 3 will decide that we have to bring another master server process to make sure we have 3 RF3. Then it may ask one of the nodes, node 4, 5 or 6, to, they also have a master server process, but they'll be in stop state. So they will ask one of the nodes to join their Raft consensus group, and since the master metadata is going to be small, it can easily replicate the data to the other node and then join them to the replication group. Now again you will come back to having 3 master server process instead of node 1, now node 4. So similar case, if node 2 goes down, it can again, node 3 and node 4 can decide, okay, we need another master server process, and then they can include either 5 or 6, or even it can include 1 if that is back online. So that is how the master server process can become master on any node, but at least maximum based on the replication factor. If you decided by default 3 replication factor, out of 6 nodes or 9 node or 12 node, how many ever node cluster you have, at least 3 nodes should have the master server process, and that can be any of these 3 nodes depending on the election process. It can decide. There is no hard coding or anywhere that you need to have master server process running only on the first 3 or next 3. So it randomly chooses wherever it wants. Although there are some advanced settings where you can dedicate master server process to a set of nodes where you only run the master server and not run the T server. Basically you don't host the data there, only you host the metadata, but that is very rare scenario. I don't see any real use case where you want to get that kind of setup unless you have like some 60-90 node cluster, which I don't think is a recurring or frequent use case. So for a better understanding, to simplify things, if you have a 6 node cluster, you're going to have one 3 nodes acting hosting a master server process. One will be primary master server process and 2 will be followers. If node fails, the master server process on that will have to shift to another node. So yeah, let's continue to the next one, which is the T server process. Now we have talked about master server process, which is hosting metadata and other activities it is taking care of. That, but the actual data processing, the user requests are handled by the T server process. And this T server process needs to have understanding about how the data is available on different nodes, and then it has to collect the data from the respective nodes and send it to the user connection or the client connection. So now T server process is on all the available nodes. So here if we have 6 nodes, T server process will be running on all the 6 nodes. So if node 1, 2, 3 is having master server process, here it will also have a T server process, whereas node 4, 5, 6 only just have a T server process. A master server process generally doesn't have much load, so that is okay. You can run both master server and T server process on same nodes, and you should not see any impact. There should be hardly 5% use CPU or resource usage. It will not be much. So you not see any difference running T server and master server process on the same node. So I hope that gives clarity how the master server and T server process based on the reference architecture. Hope that gives you more clarity. And the other important topic which we talked about was tablets. So I think that is a core basic idea behind the distributed architecture, right? So you have your table, let's say 100 GB, and or you can consider more like in terms of rows for better understanding. If you have 10,000 rows, the 10,000 rows are sharded. Let's say it's an identity column starting from row 1 to row 10,000. Then that may be broken down into 1500 or 1800 depending on how much, and it will store on each node. So first node may have 1500, second may have 1500 to 2000, or 3000, 3000 to 4500, 4500 to 6000, 6000 to 7500, and then 7500 to 10,000 maybe on the node 6. So the data will be evenly sharded at the beginning and distributed across all the nodes. And we already discussed about initial part where how the tablets are distributed. So now for the same example, if we have 6 tablets and the distribution as what I explained, 1 to 1500, 1500 to 3000, so each node has one tablet with different data ranges. Now we have a replication factor as 3, which means each tablet should also maintain another 2 copies of followers. So if node 1 has range tablet which is containing data range of row 1 to 1500, that will be primary on node 1, whereas its followers will be on node 2 and node 3. It doesn't necessarily have to be node 2 and node 3, it can be node 4 and node 5. So at least any 2 nodes should also host the tablet 1. So maybe to better understand that 10,000 rows divided into 6 tablets, tablet 1, tablet 2, tablet 3, tablet 4, tablet 5, tablet 6. So tablet 1 is primary on node 1, tablet 2 is primary on node 2, by same way node 3, node 4, node 5, node 6 has tablet 3, 4, 5 and 6. Now node 1 has tablet 1 primary, but it can also have node 3 follower and node 4 follower. And node 1 tablet 1's follower can be on node 2 and node 3. So at least each tablet should be having 2 followers including one master. So if you are getting a client request for a row ID of 10, and based on the metadata it knows, like the connection will be load balanced and it will be hitting any one of the nodes. So generally if it is smart enough, it will go to the node 1 because node 1 has a tablet which contains the data 1 to 1500. So, and since I'm selecting the node data for value 10, it should go to the node 1, and from node 1 it will, because it's a primary, because node 2 and node 3 also may have the follower data of the same data range, but by default it goes to the master leader only. So node 1 gets the request, it picks up the row number with ID value of 10 and it return back to the client. Also there are some settings wherein you can say I want to explicitly read from the follower. So in that case it can go to node 1 or node 2 or node 3 if both all of them have the tablets, one as primary node 1, node 2 and node 3 as followers of tablet 1. The node 2 or node 3 can also give the data and it doesn't have to go to always node 1. So that is how internally it can take care, depending on it is an explicit option that you will have to specify, telling that I want to read from a follower, I do not want to always go to leader. So that kind of options are also available. So now let's discuss about replication factor. Yeah, we have touched based upon few times. I think it should be clear to now you by. So basically it is about how many replicas or copy of the data you want to maintain. So if it is a replica factor of 3, basically 3 copies of your data should be there, and one will be as read and write and 2 will be read only, or explicitly you have to read from them. So the tablet 1 will have 2, tablet 2 will have 2, another 2, likewise. So every shard or tablet will have at least 3 copies, one is a primary copy and 2 follower copies. So in this case 6 tablets ideally will have 6 into 3, that is total 18 tablets will exist. Basically tablet 1 is duplicated 2 times, so tablet 2 is duplicated 2 times. So that is why instead of 6 tablets you total have 18 tablets. 6 into 3, 18 tablets. Again, if you increase the replication factor to 4 or 5, your tablet count is going to increase accordingly. So the tablet 1, which was earlier there on node 2 and 3, if RF is set to 4, it will also go into 4 or 5 or 6, any other node. So you will have 3 additional copies instead of 2. You can increase further by replication factor of 5, then it will have to maintain total 5 copies, 1 primary and 4. So all these things are possible, but most use cases generally follow replication factor 3 that should serve most of the purpose, unless you have some very special requirement. And let's talk a little bit about Raft consensus. So basically now you have, for tablet 1, if you take example, they have 3 copies. Now the 3 copies, and we are saying node 1 goes down. Now there are only two copies of the tablet T1 is available, which is on node 2 and node 3. So earlier node 1, 2 and 3 form a Raft consensus group. Now once the tablet node 1 goes down, the Raft consensus group becomes aware that the tablet on node 1, which was primary, has gone down. Now 2 and 3 will decide and conduct an election depending on the node which has the latest data. That node is going to become the new master leader. So the new master leader, let's say, has become 2 for tablet 1. Earlier it was master leader for tablet 2. Now it is master leader for both tablet 1 and 2. And there is some certain time period for it. Let's say it's 5 or 10 minutes. So after 10 minutes also, if node 1 doesn't come online, so node 2 and 3 may then decide, okay, now if there is any failure with node 2 and 3, it is possible that the tablets are going to have single node and that will cause application impact. So they'll decide, okay, it looks like node 1 is not going to come back online any soon. They may decide that no, tablet 1 now only has 2 copies. Another copy of tablet 1 also has to be created, and it may choose one of the 4, 5, 6 nodes depending on the number of tablets and the load they have. They will join any one of them into the tablet 1 Raft consensus group, and then they are going to copy the tablet 1 data there, and then again you will have tablet 1 in 3 copies maintaining RF factor of 3. So I hope that gives you some better understanding about the replication factor and the Raft consensus groups. And on the top, if you see, we have represented something called YBA control plane, and also in the DR we have represented another YBA control plane. Although you may not be understanding what exactly is a Yugabyte Anywhere control plane, it is an orchestrator where you can start the installation, and that installation can push the install on the rest of the nodes, and you can do addition of nodes, removal of nodes, you can configure backups, you can look at various metrics, and you can send out alerts. A lot of things that you can do. It's basically a GUI from where you can do all the orchestration, monitoring, alerting, backups, the many things that can be done. So I think you will get better understanding, and we are going to spend a lot of time in understanding what is this Yugabyte Anywhere control plane, because as I mentioned, we are going to configure backups, restore their point in time recoveries, look at various metrics, setting up alerts, creating users at the YBA control plane. There are a lot of things that we do in the control plane, so we are going to spend a lot of time, and you'll definitely get more understanding of the YBA control plane in future. So one last item that I want to talk about is the smart driver. So now in distributed architecture you have 6 nodes, and if you have a application which want to connect to this particular primary universe or cluster, you don't know which node to connect, because your data is sharded and tabletized and stored on each of the 6 nodes. So the example which we have taken, you have 10,000 rows, and you have 1 to 1500 on node 1, 1500 to 3000 on node 2, and so on, right? So now I am requesting for data for id value equals to 10, which is the primary on node 1. Now the connection has to ideally go to the node 1, uh, and unless there is a driver which is capable of understanding that there are 6 nodes and the connection has to be established load balanced across all the 6 nodes, the regular Postgres driver may not be able to understand this. So Yugabyte provides a Yugabyte smart driver which is capable of understanding the distributed architecture, how many nodes are there, and then based on the metadata and the load on the servers, the connections are sent to the appropriate nodes. So if there are 1,000 connections coming, it may send some 200 to node 1, 200 to node 2, node 1 to node 3, and so on. So it will try to balance the connections across the different nodes, and also depending on the metadata, it may send the request to the appropriate node where the data is locally available. Because if the ID value equals to 10, and if you're not going to send the request to node 1, then mostly other node has to request node 1 to send the data, and then it is unnecessary a lot of network work, right? So it is smart enough to understand where the data locality is available and try mostly to send it to the appropriate node. So another thing here to consider is, here I have represented two universes. So basically in traditional production for a critical application, by default it is providing you a high availability. If one node goes down, you still have your data on the other two nodes. So automatically they are making a decision and promoting the respective tablet on the other nodes, and continuing your application is not seeing any impact. However, there's possibility that entire primary site may go down for whatever reason. It can be a issue with your data center, network problems, a natural disaster or anything. You still need to have another region where you have all your data replicated, which you can invoke during a disaster recovery. And also you may conduct periodic BCP drills to ensure that you are able to, your DR is in a working condition where your applications are working. So there is a feature called X cluster replication or X cluster DR, where you can have that configuration where you can do few or all databases, few or all tables replicated to your DR site. So DR generally means every database, every table should be replicated. So that is typically X cluster asynchronous DR kind of thing that has come in latest versions of Yugabyte. So if you have 6 nodes, ideally you should also maintain 6 nodes at the DR location, and the data will be automatically replicated, and the replication is as per tablet basis. So if you have 6 primary tablets, the 6 primary tablets are responsible for sending their log records to the respective nodes, and it doesn't have to be one-to-one mapping. You can have a 6 node primary universe, and you can have a 3 node primary universe, and during a disaster or a BCP drill you may want to add additional nodes as a preparation, where you think you still have your SLA allows you to spin up more nodes, have time for doing all that stuff. And another thing is, you can have your DR, if it is in a non-cloud infra, you can have with smaller configurations to just handle the synchronization. When you invoke the DR, you can upscale those nodes so that you save on the cost. So this is a typical reference architecture diagram which you can use for critical production workloads. And one last thing here is, your applications can run from anywhere. So if your databases are, if primary is running on premises, your applications can be on in cloud, and they can connect from cloud to on-premise data center, and then using smart driver they can load balance and get the data. And also you can have your backups offloaded to your S3 or other object storage solutions, Azure Blob Storage or any other storage solutions. You can store it on a, if you have local NAS backup storage, you can store it there, or wherever you want you can store it, but all that storage should be centrally available for all the nodes and your control plane. Your control plane is going to orchestrate and going to take the data from respective nodes and going to transfer to the target location. So hope that gives a good understanding about the architecture, the core components, what we discussed, and how they translate into the reference architecture. So yeah, let's continue further into the other topics. Thank you.